So on Friday we went over Newton's second law as it applies to systems. A system is anything that has more than one mass or more than one part that is going to be accelerated by the net force. Right? Some things we have to remember about systems is that all parts of the system have the same what? They have the same acceleration. There are going to be different internal forces acting on each part of the system, but in the end, they all have to accelerate at the same rate because they're all connected. All right? So if we're looking at this situation here, and they're saying calculate the acceleration of the tire, if the mass of pail B is increased to 12 kilograms, okay, so that's now 12 kilograms. We don't change the mass of pail C, which was 6 kilograms. Okay, and the tire is still going to be 20 kilograms. Okay, we have to find all the forces. Okay, so this one's going to be 117.72, right, newtons. And this one will be 58.48? 86. Right, newtons. All right, and we just did that. We found each of those by doing this, Fg equals m times g. All right, so we've got those forces of gravity. What do I do next?
Find your net force.
Find my net force. And I'm going to use the vector sum of all forces to do that by kind of simplifying this diagram. So I have 18, I have 38 kilograms of mass in the system that's all accelerating together. All right, I'm going to have 58.86 newtons going this way, and it's not really to scale, but 117.72 newtons going the other way. All right, now when I do that, that's going to mean that my net force is 58.86 newtons this way. All right, now what do I do? Divide it by the mass. Which mass? They want the acceleration of the tire. The whole mass. Okay, that's that wording trick I told you might come up. Right? This one says calculate the acceleration of the tire. It doesn't say calculate the acceleration of the system. And then people go, oh, I just divide by 20. No, I still divide by the whole mass of the system. Right? So acceleration will be 58.86 divided by the total mass of the system, 38 kilograms. Okay, and that should come out to 0.68 meters per second squared. But this time, because they asked about a particular part of the system, what can I put on that answer? A vector, right? I can't put that on if it's like what we did originally, which was calculate the acceleration of the system. I can't put a vector on that because one of the pails moved up, one of the pails moved down, and the tire moved to the left. Right? Well now, okay, they're only asking about the tire, so now I can in fact say that the tire has this magnitude, which it shares with all the other parts. Okay, but it's going to be moving to the left. Question?
58.86 divided by 38 gives you 1.5 meters.
Whoops, sorry, I'm looking at the wrong answer. I was cheating. You're absolutely right. Okay, that's for question number 2. All right, so if the tire in example 3.11 is replaced by a car tire of 15 kilograms instead of a truck tire of 20, calculate the acceleration of each object. Now, I'm assuming that means everything goes back to the original setting of 8 and 6, not 12 and 6. Okay, it doesn't change really anything we do? Nope. Okay, we still calculate the forces of gravity on each side, okay, divide by the total mass of the system. As long as we remember that about systems, that's the thing people forget. Accelerations of all parts are the same. Combine the masses when dealing with the net force. Okay. Okay. This next one is an example of what we call a static condition question. All right. I want you to write it down, and then we're going to walk through it together. Okay. So in this example here, that's not what I wanted. That's not what I wanted. We've got this sign. 35 kilograms. Okay, now, it's being suspended by two different cables. The first cable is angled 55 degrees below the horizontal from one wall. So I'm going to say that that wall is going to be over here somewhere. Okay. And that cable is going like this. Okay, so that's my first cable. And the second cable is horizontal and is attached to a different wall. Okay, so this is cable 2, and this is cable 1. Everybody all right with that? All right. They want to know what force is cable 2, that's this cable here, exerting. And they don't give us anything else. They tell us it's two cables, they give us one angle and the mass of the sign. Doesn't seem like very much information, does it? So, what do I need to realize about this sign that can really help me out right off the bat?
It's experiencing the force of gravity.
Okay, that wasn't what I was thinking, but you're absolutely right. It is experiencing the force of gravity. So if I start doing a free body diagram, okay, and start putting my forces on, I would have a force of gravity here. Okay, so 35 times 9.81, so 343.35. Okay, what do I need to know about this sign that helps me out?
It's not moving.
It's not moving. That's what static means, right? Static means unchanging, okay, or not changing. So what's the net force in this question? Right. That's the most important piece of information I can get to start this question. My net force is 0. That means all the forces that are acting on this sign, and there are many, add up to 0. Okay. What are the forces acting on this sign? Gravity is one of them. What else?
Tension from the two cables.
Yeah, the tension from the two cables. Okay, we've got cable 2 pulling to the right. Okay, I just said Evan again, didn't I? I'm sorry. I've done that to you now what? A dozen times at least?
Probably.
It doesn't make it right, I'm sorry. All right, so I've got cable 2 pulling to the right. Do I know how hard? No idea. That's the thing they want me to find. I need to know the force pulling to the right, and I have no numbers really other than this force of gravity to do it with. Okay, so there's also this cable that's pulling on the sign. What do I know about that cable? It's angled. What does that mean?
Pulling up and to the left.
Exactly. It has a horizontal and a vertical component. Okay. That line there is going to be its vertical component. How big is it? Keeping in mind what we said was the most important thing in this question.
It's going to balance with the force of gravity.
Exactly. The net force is 0. That means the forces up and the forces down have to be equal. And that's the only thing that can be pulling the sign up. Okay? The other cable's horizontal. It doesn't have a vertical component, so it can't offset gravity at all. Okay? This has to be 343.35. Okay, I now have a triangle, I know an angle, and I know a side. Can I find out all the other sides?
Yes.
Okay. How will that help me get the tension in cable 2?
You find cable 1 and then you do the opposite of net force, so it wouldn't be.
Do I find cable 1 or do I find the horizontal component of cable 1?
Horizontal.
The horizontal component. Okay? This cable pulls this way. That force there, the hypotenuse, the cable, can't offset 2. Only this offsets cable 2 because they're in the same direction. Okay? So I'm breaking this down. This isn't just a static example, it's a vector question. And our static examples are almost always vector questions. Okay? Where we have to do some horizontal and vertical, okay, kind of stuff. So I got to find this side because it's the side that pulls to the left. Okay? Owen said right away that it's pulling up and to the left. Okay? Well, the left part is offsetting to the right part, which is cable number 2. It can only pull to the right. Since the sign doesn't move, cable 2 and this are equal. All right, so I've got the opposite side. I'm looking for the adjacent side. So if I'm going to find the force horizontal, okay, I'm going to have to go, I'm going to have to use tan, right? And it's going to be opposite over adjacent. So the tan of 55 is going to equal 343.35 divided by the side I don't know. Right? So if I want to solve for the side I don't know, I just have to cross multiply it. Okay? So the force horizontal will be 343.35 divided by the tan of 55. Okay, so the tension in that cable is, I think we only have 2 significant digits here, 2.4. Yeah, 2.4 times 10 to the 2 newtons. And that's it. It asks for tension, so I don't actually have to put a vector on it. I could say to the right, and I wouldn't be wrong. I know it's Monday morning. Okay, does everyone follow what we did there? All right, so in a static example, it's going to seem like they don't give you very much information. Now people are shaking their heads with the dad joke. Okay, good. All right. Okay, that's the piece of information that we get in a static example. Right? And it's important because then we know acceleration is 0, we know what all the forces add up to. That's an important piece of information. We can do a lot of work with it, which is what we did here. We understood that because there's no net force, the forces up and the forces down were equal, the forces left and the forces right were equal. Okay? And that allows us to determine those forces that we don't have. Okay? Is that making some sense? Okay, here's a pulley question. So now, you've got a 4-kilogram block sitting on a level surface. It's connected over a pulley to a 5-kilogram block. Calculate the acceleration of the 5-kilogram mass. And there is 32 newtons worth of friction on the table. So between the 4-kilogram mass and the table, there's 32 newtons worth of friction. All right, give you a few minutes on that. All right, so first thing we want to do is put our forces on here. All right, so we've got 32 newtons worth of friction acting back on the 4-kilogram mass. What other forces are acting on the 4-kilogram mass?
5-kilogram block.
Right, the 5-kilogram block pulling it this way, which is actually a force pulling on the 5-kilogram block. That force would be gravity, okay, and it would be 48.7. No.
49.05. 49.05
newtons. Okay, so I've got that force. Are there any other forces acting on the 4-kilogram mass?
I was thinking gravity, but wouldn't that be offset by the table?
It would, but they're still there. Okay, so yeah, gravity and the table are acting on the 4-kilogram mass. They offset each other because the 4-kilogram mass isn't moving up or down, so we don't really need to draw them on there. Okay, we can recognize they're there, but we wouldn't lose marks for ending our free body diagram like this. Okay, all right, can I simplify this free body diagram?
Yes.
Yep. Okay, we got 9 kilograms worth of mass being pulled this way by 49.05 newtons and resisted this way by 32 newtons. Okay, that's what's going on here. Can I calculate my net force? Okay, so F net is going to be 49.05 minus 32, so that should be 17.05 newtons. Is that right? That seems about right. Okay, so I've got my net force, and I want to calculate the acceleration of the 5 kilogram mass. What do we do next? Ethan. F net divided by M. Which M? 9, right. Okay, I got to divide by the entire mass of the system. And so by 9 kilograms. Alright, so we're looking at we only have one significant digit, 2 meters per second squared. Okay? Down. It did ask about the 5 kilogram mass, so I can put a direction on it. Okay? Alright. How are we feeling about these questions? Okay? Like, they're going to get a bit more involved as we go, okay? Like that static question was the first time you'd ever seen one like that, right? It's a little bit intimidating at first, but what we're going to do is just keep showing you different situations in which Newton's second law applies so that you can really start seeing into them. Okay? And then when you see something like that, even if it's something we haven't done before, you can look at it objectively and go, oh yeah, okay, I can figure that out. I can draw the forces on there and figure out where to go. Okay? Once you have the experience, then that becomes easier. Okay? All right, we did one like this last week. So the total friction on the system is 120 newtons. The friction on the first block, the 40 kilogram block, is 48 newtons. I want you to calculate the acceleration of the 40 kilogram block and the tension in rope B. And see what we remember from these multiple mass system questions. All right, so first thing, calculating the acceleration of the 40 kilogram block. The easiest way to do that is calculate the acceleration of the whole thing. Yeah, okay, that's the simplest way. So if I just simplify this diagram down to 100 kilograms, right, it's being pulled this way by 150 and this way by 120. That's it. Okay, that's how I would get the acceleration. So F net, right, would be 30 newtons to the right or forward, okay, and then the acceleration would be 30 divided by 100, okay, so we'd have 0.3 meters per second squared. Actually, we'd have 0.30 meters per second squared right. Okay, everybody all right with that? Okay, having that acceleration is important because for part B, where I'm calculating the tension in rope B, okay, I need that, because I got to calculate the net force on individual boxes to solve that part, right? Sometimes we solve the system question as a whole, and sometimes we break it down into smaller pieces and isolate parts of it, right? So to do part B, I'm going to isolate one part of it, and that's going to be the 40 kilogram box, because that's the easiest one to do it with. I do one less calculation with that. I could also solve it with the 60 kilogram box, but I choose not to. Okay? All right. So I got my 40 kilogram box. Okay, first thing I want to calculate about my 40 kilogram box is the net force acting on it. So that's going to be mass times acceleration. So that'll be 40 kilograms times 0.3. So the net force acting on it is 12. 12 newtons forward or right. I said right before, so I should say right now. Okay, 12 newtons to the right. Free body diagram. I got 150 newtons here. I got 48 newtons worth of friction here. And then I have the tension in the rope from B. Okay, so can I calculate the tension in B? I know the net force, and I know 3 out of the 4, or yeah, 3 out of the 4 things. So F net for the 40 kilogram box equals B plus 48, negative 48, okay, plus 150. Right, so I'm just going to bring the 48 and the 150 over, and that's going to look like this. 12 minus 150 minus negative 48 is going to equal the tension in the rope from B. Right, so 12 minus 150 minus negative 48. All right, so negative 90 newtons. Right? I don't have to put a negative on that because it asked what was the tension in cable B. 90 newtons will do just fine. And could I have done that with the 60 kilogram block as well? Yes, I could have. All I would have to do was subtract 48 from the total friction, okay? Because they said the friction on the 40 was 48, so if I subtracted that, that would give me the force of friction that was acting here. Okay, which would be, what, 72 newtons? Okay, and then I'd have this being my driving force forwards, and I'd be able to calculate it after I calculate the net force.
And that force for like the second part, would not be 150 minus 48.
For the second part?
Yeah.
No, because I also have this one,
Oh.
right? I calculate the net force on just this mass by just going 40 mass times acceleration,
Okay.
right? Because I can't go 150 minus 48 because I still have this other force here that I have to calculate. Yeah? All right, questions on that one? Okay, I would like you guys to try a few from the digital workbook here. I'm just gonna pick them. Okay, I would like you guys right now to try 18, 19, and 20. 18, 19, 20, and 21. Okay, so 4 questions, 18 through 21. I would like you guys to try. And then we're going to talk about inclined planes, okay, which is another type of Newton's second law question. In fact, it's my favorite type of Newton's second law question. All right, so we'll talk about inclined planes after you do 18 through 21. Okay, now, a little word of warning for these. Okay, I'll make it a little bit bigger here. If it gives you, like in question number 21 here, it says a 725 Newton student. What did they give you? They gave you the weight. Because mass would be in what? Kilograms. Okay, so what force is your weight? Gravity. So when it says something is this many newtons, not being pulled by this many newtons, is this many newtons, they're telling you it's weight, which is the force of gravity. So you can get the mass from that number because you know what G is, right? That number is calculated by going M times G. All right, so when they do that, they're trying to trick you, but know that they're also giving you one of the forces in the question. Okay? All right, I think I made that too big because now you can't see all those guys. All right, I'll move it up here in a minute, guys, but you can get started on 18, 19, and 20, okay? And then I'll move 21 up in a second. Okay, so for number 18, okay, we know that VI is 24.0 meters per second. We know that VF is 0 meters per second. We're looking for D. Okay, and we also know that when we slam on the brakes, 1,500 kilogram car is slowed by 18,000 newtons worth of friction. Okay, so once you slam on the brakes, is your engine pulling you forward anymore? Once the wheels lock up, which is what's going on here, or even if they don't lock and you've got the brakes on, the engine is no longer providing a forward force on the car. So what's my net force? 18,000 newtons backwards. Okay? The brakes are the only force on the car, that's why the car stops. Yeah, sure, gravity is there, but so is normal force, and it says it's a level road, so, okay, actually, it doesn't say it's a level road, but we have to assume it's a level road, okay, because it was uphill or downhill, that's different. So, we've got this force. This is our net force. Anytime you slam on the brakes, or your car runs out of gas, or something like that, the force that brings you to a stop is friction, and as long as it's a level road, it's the only force acting on you. So, by default, it's the net force, that's the vector sum part. Okay? It's the only force acting that makes a difference. So, I can calculate my acceleration by taking that 18,000 newtons and dividing it by 1,500 kilograms, and that will give me one more piece to use over here to calculate my displacement. Okay?
So does this kind of go back to our unit 1 almost?
Yep, and we said that was going to happen quite a bit in this unit because we're dealing with accelerating objects, so we're going to be going back to those acceleration formulas all the time. All right, so the acceleration experienced here is 12 meters per second squared backwards. Right, now I've got that. Well, now I can calculate D. Right?
Okay.
So if I plug that in, manipulate for D,
Yeah, because I just didn't know that we were allowed to use equations from, like I didn't know that we
Oh,
were
yeah.
using equations from the first unit. So
every equation, once we learn it, every equation is game. Okay? We won't use V equals DOT very much in this unit because everything's accelerating. But every equation we learn is going to be game once we learn it. Okay? All right, does that make sense?
Yeah.
So we got 24 squared over 24, so I guess it's 24 meters. Okay? All right. How are we doing on the other ones? Some people are done up to 21. Okay, so we still need a little bit of time then? All right, I'll give you a bit more time, and then we'll start talking about inclined plane. Okay, so I actually talked about this one the first time we went over elevator questions, okay? And I said to you, you're going to have this situation that's going to come up that seems really dumb, because, you know, everybody brings a bathroom scale into the elevator with them, okay? But this is kind of a classic elevator question. What the scale reads is how hard the floor of the elevator is pushing on your feet. We call that your apparent weight. Okay? If the elevator is if the elevator is accelerating, your apparent weight will be different than your actual weight. Okay? So if the elevator is accelerating up or accelerating down, the scale will read a number different than when the elevator isn't moving or is moving at a constant velocity. Okay? Because in either one of those situations, the net force would be 0, and the force of the floor and the force of gravity would be equal. Okay? So in those two cases, constant velocity or not moving, the bathroom scale reads your actual weight. Okay? Any other time, it reads your apparent weight. Okay? Apparent weight is a term that's going to come up a lot in both Unit 2 and Unit 3. Your apparent weight is the normal force. Okay? It's the reactive force of the surface you're standing on. All right, so they don't tell us the mass of the student. Okay, and they don't have to because we can calculate it. And that's probably something we should do right off the bat. Mass is the force of gravity divided by the acceleration due to gravity. So I should take that 725 and divide it by 9.81 to get the mass of the student. Because I'm gonna need that. Alright, so 725 divided by 9.81, the mass of this student is 73.9 kilograms. Alright, so I've got that. I can put it in here if I want.
How come we didn't use the 775?
Because that is what it reads when the elevator accelerates. Okay, so it tells me a 725 Newton student, so that's the force of gravity, that's what they weigh. Okay, 775 is how hard, is what the scale reads when the floor pushes on their feet to move them upwards. So it's two different ones, that's how I choose. Okay, so in the situation that's being examined in this question, the upward force is 775 newtons. That's what the scale says the floor is pushing up with. Okay, and then this force is 725 newtons. Okay, that's the force of gravity. Since the force of the floor is greater than the force of gravity, the elevator is moving upwards. In fact, it's accelerating upwards. All right. So, can I calculate the net force? Yeah. Okay. So my net force is going to be 775 minus 725. Okay. So a nice easy calculation, 50 newtons. Can I calculate the acceleration of the elevator and the person in it? Yes. Okay, so 50 over 73.9 should give me 0.677 meters per second squared up. Should have a vector on that answer. Okay? Now, contextually, is there some stuff to think about in that question? Yeah. Okay, it doesn't give us the mass, we have to figure out how to get that. We've got to understand which force is up and which force is down, okay, all of that kind of stuff. The math in the question is pretty easy. We had to divide a couple of numbers and subtract two numbers, and that was it. Okay? Most of the time in a Newton's second law question, you don't have too much complex math. Okay. All right, let's look at inclined planes. Okay. Before you start copying anything down, what's the simplest machine? A slope, a ramp, an inclined plane. Okay? Why is an inclined plane a simple machine?
It distributes the weight all along the length of the.
It does do that. It's a hill. What does it allow people to do? Okay, if we're going down, certainly we can accelerate downwards, much more safely than falling. Okay, but in terms of being a machine, machines make work easier. Do they make less work? They do not. It is impossible to make less work. Okay, you can make the work easier, but you can't make less work. Right? What an inclined plane does is it allows us to move a mass using less force to a specified height. Okay? If I wanted to move this mass to the top of this ramp, I have two options for that. Lift it and stick it on the top of the ramp, or push it up the ramp. Pushing it up the ramp is easier. Why?
Because you use less force over a longer time.
Longer distance, right. I use less force over a longer distance. The ramp supports some of the weight, some of the mass, okay, the gravity pulling on the mass of this object. Now 10 kilograms is 22 pounds. We could all lift that and put it on top of the ramp, okay? But if it was something really, really big, a ramp might be necessary. Like, let's say you're building a pyramid in Egypt and you don't have help from aliens. Okay? What do? You build ramps. Really, really long ones that wrap around the pyramid. And you get all your slaves, because you have lots of those, okay? And I'm not saying that that's right, I'm just saying that that's how it was done, okay? Not saying that's right, okay? And you get them to push these things up this ramp. The ramp's not very not very steep, okay? It just gets really, really long as you go up the ramp, okay? As you go towards the top.
What do we call it?
Inclined planes.
It's like
No, like the question, like addition was called vector addition.
Yes, these would be called Newton's second law inclined plane problems. Yeah. All right, so here's why a ramp makes work easier. Okay? This mass would have the force of gravity acting down. Okay? I mean, gravity acts on things. We can't stop that. That force of gravity in this particular situation will be 98.1 newtons. 10 times 9.81. All right? When I put something on a ramp, the ramp holds some of the weight. Okay? But because it does that, the ramp has to push back against the thing I've put on it. In the same way that right now, the floor pushes back against my feet. Okay? That's the normal force. When the surface is level, the normal force and the force of gravity are equal. In this case, they're not. If this is a frictionless ramp and I set a 10-kilogram block on it, what's the block going to do? It's going to slide down the ramp. Is it going to slide down the ramp at 9.81 meters per second squared? No. Even if it's frictionless, it's not going to do that because there's another force right here. This is the normal force. It's the force of the ramp pushing back up on the mass. Surfaces can only push perpendicular to themselves. So because this is slanted, it's no longer equal to the force of gravity. It's going to be a little bit bigger or smaller? Smaller. It's going to be a little bit smaller.
Shouldn't you draw it from the center of the block out instead of putting it towards the?
On a free body diagram, I would do that, but there's a reason why I'm not doing it, which you'll see in a minute.
Okay.
You're absolutely right. On a free body diagram, I should draw it that way. Okay? On an inclined plane, I draw it this way because here's what I'm doing. I'm drawing a vector diagram. I have normal force pushing up. I have gravity pulling straight down. Okay? You notice how I drew these two vector quantities? Tail to head. What does that red arrow represent?
Your resultant.
Which is?
Acceleration.
Be all right there, Tegan?
Yep.
It's the vector sum of those two forces. What is it?
Net force?
Net force. And look at it. This wasn't by accident. Ah, it's parallel to the plane, which is the direction it's going to accelerate, yes? See, that's why physics is awesome, because it just works. Okay? Stuff doesn't happen by accident. Okay? It just works. So we call this force, as Owen kind of alluded to, we call it F parallel. Those are two parallel lines, by the way. F parallel. Okay? F parallel is the net force between the normal force and the force of gravity for any object placed on a plane. Now, I'm going to finish my free body diagram. Okay? This is why I didn't draw these all on before. It gets kind of messy and busy looking. Okay? I would have F parallel, and if this was a frictionless plane, that would be it. That would be the net force, the vector sum of these two forces. How many frictionless surfaces do you have hanging around? None. You can't ever make a perfectly frictionless surface. Okay? So, what is there probably here? Friction, which would be acting which way?
Against the ways that you're going.
Right. So, since this thing is probably trying to go down the ramp, friction would be acting up the ramp. What if I was pushing it up the ramp? Then friction would act down the ramp. Friction always works against you. Okay? So, then if there was friction, I would put it here. And then I could do a Newton's second law, do a sum of all forces thing. Okay? In the end, this is still, like if I'm putting all this on this vector diagram, if I had a force of friction, I would do this. Okay? So I'd have normal force, gravity, okay? That adds up to F parallel, then I put friction on there, and then this little bit would be my overall net force. That gets really, really busy looking, okay? Which is why we don't do that. Okay, we calculate what F parallel is, and then we put all the forces that act along the plane on there.
So you
Right.
have two F parallels?
Nope.
Oh, you
I-
just use it.
Just use one, that's the only one. That way I don't have to worry about gravity and normal force. This is what I have. I would have F, force of friction, and then if there was an applied force up or down the ramp, I would stick that on there. Okay, so if this was, let's say, somebody pushing this thing up the ramp, okay, then I would have friction acting down the ramp, and an applied force acting up the ramp. Okay, there's really only ever going to be three. Okay, you've either got a force up the ramp, a force down the ramp, parallel, and friction. That's the most there can be. All right, so there's only ever really going to be three. Everyone with me so far?
Yeah.
Okay, so this little internal triangle applies to every single inclined plane. Now, they told me this incline is 30 degrees. So what do you suppose this angle here is? 30 degrees. Okay, so on the inside of an inclined plane, you always have that vector diagram being given. Normal force and gravity, gravity is always vertical. Oh, thank you.
Thank you.
You want to go get cleaned up, Pete?
Can I go to the?
Yeah, just go to the washroom. I'll take care of that, okay? All right. So this internal triangle is always the same for an inclined plane. This angle is always the same as the angle of the incline because it's how far offset gravity and the perpendicular normal force of the plane are. Okay, so it always has to have the same angle as the incline of the plane.
So is that little triangle or an angle triangle?
It is, yep, this is a right angle triangle here. Absolutely. All right, so we'll talk more about inclined planes tomorrow because we're almost out of time. We will have a quiz tomorrow, okay? Have some trickier Newton questions on it. Okay, I'll post it today at 3:30 as always.